Hello, I'm Pablo Martinez, and I will present my work with Aurelia on universal bounds inspired by chaos. Yeah, feel free to interrupt me whenever you want. So this is an overview of the topics that I want to cover in the presentation. I want to start giving you like the goal of the project, and after that I want to give like some introduction, which is hopefully pedagogical to quantum chaos and the bound of chaos, which can be interesting to many people, and see what features of this bound, what ideas can we extend to bound other dynamical quantities. After that, I want to exemplify the bound that we find on the spectral form factor in different systems and compare it with other physical bounds, like, for example, quantum speed limits, and end with some conclusions. Okay, so this is the Maldacena bound, essentially in a paper in 2016, and Maldacena synchronous Stanford conjecture that the Lyapunov exponent cannot be bigger than 2 pi over beta. So let's break this bound down into its main ingredients. So we have on the left-hand side here, we have quantum chaos appearing, right? Quantum chaos as diagnosed by the Lyapunov exponent, which comes from the OTOC. Of course, this I will introduce it afterwards, right? And just taking a look from the outside. And then we have the inequality itself, right? This inequality comes from the region in which this OTOC is analytic, when we take the time to be complex, right? So remember that a function is analytic if it is infinitely differentiable, but to our purposes, we will consider a function analytic if it is well behaved, so no divergences and so on. And the region in which this quantity is analytic turns out that it's something like this, right? And this is what allows us to bound the quantity. I will go more in depth into this. And lastly, we have the bound itself, which is universal because it only depends on the temperature, right? And so one parameter, like it doesn't depend on the specific fine structure of the system, and it is saturated by black holes. Indeed, this was what led Maldacena to conjecture it. But yeah, I will not go too much into this way, but of course there's plenty of research in this line with ADS-CFT correspondence and so on. So the question that I want to answer through this talk is this structure, right, is nothing very specific to the OTOC itself, or neither to chaos. So can we find similar bounds on other dynamical quantities, which also will be universal? And if we can, do they only happen in chaotic systems? That is what I want to answer. So first, let me begin with a brief introduction to quantum chaos, and in particular, why are we interested in quantum chaos? What makes quantum chaos interesting in some sense? And on the one hand, we have that Heisenberg's uncertainty principle would not allow us to measure the initial conditions with arbitrary precision. So, and also measuring in the quantum world is a whole different business to measuring in the classical world. And furthermore, the Schrödinger equation is linear in the wave function. So we do not expect really the exponential growth in the same sense as we do in the classical case. However, in the other hand, we know that the classical world should arise through the correspondence principle at some limit of the quantum world. So we have these two things clashing together, right? These two ideas seem to not match, right? And to make them match, the physicists, like back in the 80s, in the first studies on quantum chaos, said, okay, let's study quantum systems that have a chaotic classical limit and see what features do they present. One of the early milestones on this study was that of they realized that these physical quantum chaotic systems, like for example the kicked-up chaotic billiards, of course, I will go more in depth in the important ones, were having some very similar properties to abstract ensembles of random matrices, right? And this was also very interesting because it connected, in some sense, the world of quantum chaos, which was, if you want, being born in those days, with the study of random matrix theory, which until then was only in the context of pure math or mathematical physics, if you want. So this is known as the BGS conjecture, and yeah, allow us to connect these two worlds. So let's see what are the features of these quantum systems which have a chaotic classical limit. The main thing is that the energies that we get are correlated in some senses, right? One of these correlations is what we call level repulsion, in the sense that the energy levels, it's like they repel each other, right? They do not want to be together. So we will not have degeneracies in these chaotic systems. Also, these systems show ergodicity in the sense that they explore the full phase space given a long enough time. And there are some signatures in dynamical quantities, which I will introduce throughout the talk. So just to give you a flavor of what is that these quantum chaotic systems show, one of the properties is this level repulsion, right? So here I'm plotting essentially the level spacing distribution. So I'm taking the difference between the energies, the consecutive energies, right? And essentially doing a histogram. So if the system is not chaotic, we expect the behavior in blue, right? So it decays, if you want, monotonically. And the probability density of having two exactly the unit levels is 1. So it's pretty big that we can have, right, degeneracies in an integrable system. However, if the system is chaotic, the behavior is pretty different. It's the one that I'm displaying here in red. And you see that the probability density of having a spacing of 0, so two exactly the unit levels, is 0. Also, here I'm illustrating this VGS conjecture because this analytic line corresponds to the result obtained by from these abstract ensembles of random matrices, and the histograms have been computed for one from one physical system. Okay. So good. I don't know if there's any question on this.
Yeah, Pablo.
Yeah.
So can you just briefly distinguish quantum chaos and classical chaos again? So is it just that the chaos is pretty much the same? It's just whether it emerges from a quantum system or a classical one?
I would say that the difference comes from, let me see. So okay, 1 second. One second, please. And now should connect up. Yeah, now you should be able to see. So let's say in the classical case, right? So we would expect, right, if we have to imagine this is the phase space of our system, right? And we have two initial conditions that were initially very close together, right? These two. So with time, they diverge exponentially, right? So they separate exponentially fast, right? So one expect the distance between these two to grow like a positive exponential, right? And this exponent is the Lyapunov exponent. This is in the classical case, but in the quantum case, everything it's much more difficult because you cannot. If you cannot measure these individual trajectories, right? So how do you do this? Because the concept of a single trajectory in the quantum case it's much more difficult, right? So what people did was say, okay, let's take a quantum system, right? Some wave functions, some Hamiltonian and so on, which we know that which we know that when we take the semi-classical limit, right? So h bar going to 0, it has chaotic features, right? And then from this system, let's see, okay, what are the features that these systems present, right? What are the features which are typically called signatures of chaos, quantum signatures?
So you say that when h bar goes to 0, you have pretty much the standard classical chaos where you can define a little. Okay, so it's just it's in the special limit of the.
That is why it's not very easy to study it. Of course, one may find some analogous quantities, right, in the quantum world, which I will go right now to it. But one needs some special. to define this one needs special correlators, which I will introduce now. So it's not easy in that sense.
Yeah, but that's helpful actually.
Yeah.
What you've just drawn it's very helpful. Thanks.
Okay. Yeah. If there's any more questions, or if not, I can follow. Okay. So yeah. Now I want to go to these dynamical signatures of chaos that I was talking before. So how can we witness quantum chaos in the dynamics? So one of the ways, which is very studied nowadays, is that of out-of-time order correlators, or OTOCs, which were originally proposed by Larkin and Ovchinnikov in the late 60s, but have only exploded recently now. So the idea is that we want to measure how much two Hermitian operators do not commute, right? And to do so, we take their commutator, we square it, and we trace over it. We average over it in some way, right? And you could ask, what does have to do with chaos? And you would be right. I can give you some semi-classical argument. So the idea is, if we take A to be the position operator and B to be the momentum, right? We know that in the semi-classical limit, this commutator will go to the Poisson bracket, essentially. And when we compute the Poisson bracket, we will find that this Poisson bracket will be the derivative of x at time t with respect to the derivative of x at time zero, sorry, with and this quantity in the classical world grows exponentially if the system is chaotic, right? And this defines the Lyapunov exponent and so on. And this is how you can make sense of these OTOCs, right? Of these quantities. I don't know if this answers a bit more your question, Luke. Or yeah.
Yeah, a bit. Now I'm just a bit. So when you take h bar to 0, and then on the right hand side you still have h bar.
Yeah, no, it's. I mean, the limit of h bar going to 0 is has to be taken
like a
with care. Like it's if you want. I think you can understand this as a first order expansion in powers of h bar, right? You know, the semi-classical limit will be just the first order, and you will have more terms that will contribute to your semi-classical expansion. In this sense, is in which you have to understand. It's of course also h bar is dimensional, so you have to be careful with this limit, but I mean that's like it's like a shortcut to say classical limit. Okay, so we would want to not only take the average at infinite temperature, but also include thermal effects, right? And you could think, okay, let's take a thermal factor, include it here, right? In this expression, in trace over it, and see how it behaves. And it turns out that we cannot do that. I can give more details on that if you want at the end. But one needs essentially to introduce a regularized version of this OTO. If you want, I can give more details on this. And the most common way of regularizing, there are many, is to take the thermal factor and split it in 4 and put it like this between the operators. Okay, so when we have this quantity, which is related to this C I was defining at the beginning, and if the system is chaotic, we expect this quantity to decay as 1 minus and a positive exponential. This is what defines the quantum analog of the Lyapunov exponent, right? So, any questions until here? So, the thing is that when we take this quantity and take it to complex time, right, and extend it to the complex time, we find that these beta factors change to beta minus beta over 4 minus tau and beta over 4 plus tau. So if we want all this quantity to be sure that this quantity converges, we need all of these parentheses to be positive, right? Because if not, the sum may blow up and so on. So this essentially limits our tau, the imaginary part of our time, to be between minus beta over 4 and plus beta over 4. And this is what gives the region in the complex plane that I was showing you before. So,
Hello, can I stop you there? Why do you want to make this specific transformation when time becomes time plus I tau? Where is the the physical motivation, if any?
I think the physical motivation would be, you know that you can, if you want, understand. I mean, you know this connection between between a quantum field theory and statistical mechanics, where quantum field theory would be like taking a complex or imaginary inverse temperature, right? So the partition function, the propagator are two coins, two sides of the same coin, if you want. So I think this goes back to that spirit. I do not have a physical meaning for the value of this OTOC, for example, here in this point of the complex plane. I do not have it. But I think the whole approach of taking time to be complex goes back to that, to be able to compare statistical mechanics and quantum field theory in the same footing.
But it's a bit, so you make a translation in time where you add the complex number to time. So it's not that you map time into its complex counterpart, you really add a quantity, which is
I know.
Okay.
I don't think there's as I say, a physical meaning for this quantity at an arbitrary value of the complex time. For now, you can, or at least I think of it as some mathematical trick that we can do, in which we can find some bound, and then that bound applies in the real line, which is where the things are. I mean, where we know that things work, So I don't have an intuitive idea of what that means.
But the Heisenberg operator evolves with h or with a different h?
With h. Evolves with
so
h.
In a sense, it's t minus tau that counts, right? If I
no, because when I did not write everything here, but when you put the time evolution in this operator, you see that when you put the complex part of the time, you get a positive or negative exponential, but real. So that is why the tau gets translated to the thermal factors, right?
Yeah. Mm-hmm.
Okay. Any more questions? Okay. So for now we have defined this sort of this quantity that we can use in some sense to determine this chaos, and let's see how we can bound it, right? So let's observe the argument that they did in their seminal paper. So we will have two conditions, right, on some general function of a complex variable. So let's say that our function is analytic on some half stripe of the complex plane. Here I'm using an extra parameter a to determine the width of this strip. And let's say that this function is real on the real line, just for the sake of simplicity. So what we can do is we take this region of the complex plane that we have, and through some complex map, we map it to the unit disk, right? We can do this. We can find some map that, and it turns out that this map bounds, maps this region into this other region. And if now we have that the modulus of the function is smaller than 1, we are essentially mapping this unit disk into itself, right? So no point in this unit disk will go outside of the unit disk because the modulus is smaller than 1. So we can use one result from complex analysis, which is known as the Schwarzschild theorem, which essentially states this. And at long times, when we simplify our calculations, we find this expression. So in a sense, and this I think answers a bit, well, not answers, but it has to do with what Etienne was saying. The width of this strip is setting us a a bound on the derivative of the function in the real line, right? So one does not need to have a physical interpretation for what is the quantity here, right, in the middle of the strip, I mean, in any point, in any general point of the strip, because just by this argument, we are able to bound it, right, to find some bound on it, which depends on how wide is this strip, right? And turns out that when we substitute the OTOC, what that we had before, we find some nice cancellation of this left-hand side. And we find the bound of Magdalena that they derive. But I want to stress out that at least for me, I think that this result is much more powerful than just the OTOC, you know, like it's not specific to the OTOC itself. And that is a bit where I'm heading to, because I think this formalism can be applied to bound different quantities, which are not only the OTOC, and to find universal bounds, which may be physically interesting. So what can we bound with this formalism? Well, I don't know if you have any questions, or if not. So the conditions for the functions that we can bound, the dynamical quantities, is that they should have the two properties of the theorem. So they have to be analytic on some half stripe of the complex plane, and they should be the modulus is smaller than 1 null points of the half stripe. So we can normalize them, right? And lastly, we know we need to have this inequality here, right? This inequality to be time independent, because if not, we will be having here some function of time, and here some we are disregarding terms we depend on time. So we need to find something which is time independent. So this gives us the condition that f should be something like this, right? So 1 minus and some positive or negative exponential. And since this 1 minus is nothing, it's just a redefinition of our quantity. In principle, we can bound exponential growth or decay. So here I'm representing like the space of all quantities that we could bound using these analyticity constraints. And we have, of course, the OTOC, which has been very studied in the context of the bound on chaos and so on. I want to convince you that we have found another one, which is the spectral form factor. But here is where I want to motivate you, because I think there's plenty of room in this space, and we could, in principle, find bounds, universal bounds on other quantities. The only condition that we need is that they obey these three conditions, but I don't think they are so restrictive. And so, in principle, we can bound many more things, and indeed, we can either also think of trying new domains, like the region in the complex plane being a bit different, because one would need to change the map or do some intermediate procedure, but in principle we can do this. So yeah, I don't know if you want to ask something, if you have any idea here. Okay. Yeah, if not, let's continue with the bound that we found on this spectral form factor. I'm talking a lot about it, so let's define it. And essentially, it's a quantity which captures the correlations between the energies, right? How these correlations behave. And this is the if you want the definition, right? So all of the correlations appear in this sum, right? And all of the correlations have a role in this quantity. We can also show that it is related to the partition function at complex inverse temperature, which has to do with what we were discussing before, of this imaginary part of the time or imaginary part of the inverse temperature and so on. And also it can be understood as a fidelity between two pure states, which are particularly these coherent Gibbs states, which are some pure state which has a thermal distribution. So it's not really a thermal state, but it can give us some flavor, and it can mimic some of the thermal average and thermal properties, and this is why they are interesting. And also, yes, to keep it to keep all of the things that the spectral form factor can be related to. It is also the Fourier transform of this two-level correlation function. So it's essentially, I mean, it doesn't have any information which is not present in this two-level correlation function. We are just displaying it in a different way, if you want, which may be interesting for some purposes, not us, but not our purposes. But the thing is that in the study of quantum chaos, it is very interesting, and people study this quantity a lot because it has a very clear shape, right? It starts decaying, it gets to a minimum in the deep, and grows back, right? This growth is what we call the ramp, and it's a signature of quantum chaos because it happens because of some correlations between these energies, right? And lastly, one detail is that this quantity is not self-averaging. So if we just take one realization, one spectrum, we will see that this quantity has some very fast oscillations, right? So to get a feel for this quantity, we need to average and to introduce some average over some ensemble or some range of parameters or over time. Okay. So, on the properties of the spectral form factor that are interesting to our case, we realize that it has also the same analyticity structure, right? When we take time to be complex, we find essentially this expression, so that beta gets shifted to beta plus and minus tau, and if we want both of those, I mean, if we want this quantity to be sure that it converges, we need that tau to be between minus beta and plus beta. So we have essentially a wider strip of the complex plane, if you want. We can also show that it is bounded, right, but by the values of at the borders of the region, and this induces some new normalization of this quantity, which respects the property of having a modulus smaller than 1. And lastly, there is some special time scale. I can give more details on this if you want at the end of why is this time scale, but the inflection point of the logarithm of this function shows exponential decay around it, right? We see some exponential decay, and the exponent, we call it the inflection exponent, but this decay is happening before any of the chaotic features show up. You know, like it's happening on the slope, so before any of the chaotic features show up. So in principle, our arguments hold for chaotic as well as non-chaotic systems, for both of them, right? So we find essentially a very similar bound to that of Magdalena, which is pi over 2 beta, right? That this eta exponent has to be bounded by pi over 2 beta. So now I'm going to turn to some examples. If you want to discuss something from this, something that was not clear, I think it's maybe a good time.
But here the meaning of eta is still related to the Lyapunov exponent or not?
No, it is not. It is not. It is just that, well, if maybe this can be visualized better in the examples, or if not, yeah. So the idea is that, okay, yeah. Let me 1 second. Yeah. Okay. So the idea is that the spectral form factor, right? We have it here as a function of time. It will decay, right? And then if this, if the system is not chaotic, it saturates. This is non-chaotic. Saturates already, and if the system is chaotic, it goes a bit down and then grows. And if this happens, if the system is chaotic, right? So what we are doing is essentially taking this function and doing some, if you want, exponential fit over here. Of course, this will be a logarithmic scale, right? So we are essentially doing some exponential fit here, which is where this eta comes from, right? So it doesn't have anything to do with the Lyapunov exponent. Okay. Okay. If not, let's continue. So now I want to go with some examples of this one that we. And as I told you, like this is not only particular to chaotic systems. So the easiest non-chaotic system that we can think of is a harmonic oscillator. Of course, this is the Hamiltonian. We can compute the partition function. It's pretty easy to show that it is given by this expression and by some properties of hyperbolic trigonometric functions. We find that this is the spectral factor. However, this spectral factor does not display the typical chaotic or non-chaotic shape because since this has a very well-defined spectrum, very specific, it is indeed periodic in time, right? So it is not as we had before. And we see that as we increase the temperature, this gets to lower and lower values, right? But the time scale that we are interested is here. I don't know if you see it correctly, but these stars represent this time scale around which this quantity decays exponentially. So we can show this exponential fit, and we see that it accounts for some of the intermediate time decay, right? Not the very short time, because this is not in log scale. But yeah, it describes part of the intermediate decay, if you want, this eta exponent. Okay, so when we take this eta exponent and we plot it as a function of the inverse temperature, this is what we find, right? So as we increase the temperature, so decrease beta, we see that it grows and more and more and more. And one can compute that this is exactly the exact expression, the analytical expression for this specific case. In general, I don't think we can find. I mean, we cannot find. Maybe someone can, but we cannot find analytic expressions for it. So we see that even in this very simple system, the system already, I mean, this eta exponent already respects the bound that we have derived, right? Because this is the bound, and we see that it goes and always respects it. By the way, these three lines correspond just to the three values of the inverse temperature that I was showing here. Okay, so this was an easy example with a harmonic oscillator, but we say, okay, let's see how this behaves if the system is chaotic, right? So to do so, we study on our system, which is the Gaussian unitary ensemble. It's one of these ensembles of random matrices that I was talking at the beginning. And the idea is that we sample the elements of the Hamiltonian independently, one with respect to each other. And this describes systems which do not have time reverse asymmetry, right? Okay, so here in this ensemble, we need to introduce some ensemble averages, right? And we can compute this either analytically, as is done for any, in general, in this paper over here by Adolfo and Aurelia, or numerically with the both. And we see the typical chaotic shape, the shape I have been talking about, you know? So the spectral form factor, it starts decaying, right? In what we call the slope, and then this system is chaotic, so it grows back again, right? This growth is the signature of chaos, and it is related, as I told at the beginning, to the correlations between the energies, right? But the exponential decay that we are interested in here does not care about this ramp, right? It happens. I mean, we are fitting here in the slope of the system, right? So I don't think it captures any of the chaotic features, but rather more general, right? Features which may be present both in chaotic and non-chaotic systems. Okay, so we do the same. We take this eta exponent and we plot it as a function of the inverse temperature, and this is what we find. And this has two striking facts, I would say, the two interesting things, and it is that we get very close to saturating the bound that we have derived, right? For some region of temperatures. And why is this interesting? Because, for example, to saturate Maldasena's bound, one needs, I mean, there are very few models which saturate it, like only SYK models and black holes, so some very, very special models, right? And here in the first thing that we have tried, we already get close to saturating it. So the bound may give more physical intuition, right? Or can describe some of the behavior right here close to this saturation region. Also, another interesting thing is that unlike the Hamiltonian, the harmonic oscillator, sorry, this eta exponent saturates at high temperatures, right? This happens because the Hilbert space of the random matrices that we are considering is finite, right? So we get to some point where, I mean, we can think of the thermal average as when we increase the temperature, we are including more energy levels in the average, right? So if the number of levels is finite, because the dimension of the Hilbert space is finite, we may get to some temperature in which increasing the temperature does not put any new levels in the thermal average, right? And I think that is why we see this saturation over here. Okay, so lastly, okay, we have studied one chaotic system, one non-chaotic system, but they were very different, right? So we could not compare, if you want, chaos in the same footing, right? What is the role of chaos in this bound and in saturating this bound and so on. So to do so, we have used another system, which is the quantum kick-top. Essentially, it is a time-dependent Hamiltonian, which is periodic, and since it is periodic, we can introduce the Floquet formalism, right? Which allow us to study the system stroboscopically, sorry. So at the different periods in a time-independent fashion, right? Concretely, this kick-top describes some spin S, general spin S, so S doesn't need to be 1/2, which is subject to some free precession, and we kick it periodically, right, with some periodic kicks. And this is the Floquet operator of the system. I can give you more details on this if you want in the end. So the idea is that we have two vector parameters, right? One, P, which describes the direction around which the angular momentum precesses, and if you want, the strength at which it does, and K, which describes the direction and the strength of the kicks, right? So if the two vectors point in the same direction, the system will be integrable because we will have an extra conserved quantity and so on. However, if the two of them point in different directions, the system in general is chaotic, and given that the strength of these kicks is enough, because it may not be for very low kicks, we can also manage to break time reverse asymmetry choosing these parameters in some special way. This is just to compare it with the Gaussian Unitary ensemble that I was showing before. Okay, if you want more details on this, I can give them at the end. So from this Floquet operator, this is time independent, right? It is just at one period, right? So we can get some pseudo energies, right, which we define from the eigenvalues of the Floquet operator, and of course these pseudo energies should be taken with care. Like some of the thermodynamic properties will not be well described at all by these pseudo energies because we are inputting energy to the system periodically, but for some things they are interesting, and it turns out that they can define a meaningful spectral form factor, right? So introducing some suitable average, we see that if the system is not chaotic, this spectral form factor decays and stays constant, right? It saturates to the plateau. However, if the system is chaotic, this spectral form factor decays a bit more and grows back again. So we see the signatures of chaos, right? This is how we can say, if you want, that the spectral form factor here, and the kick-top that we have has chaotic behavior, right?
So but that's a fake structure form factor, right? It's the one with the quasi energy, not
yeah. It's like a pseudo spectral form factor. Yeah, but it turns out that we actually I was looking at references on this because this Floquet formalism has been pre-studied. It turns out that if you define a partition function from these pseudo energies, it does not make sense. It does not capture the thermodynamic properties because you are inputting energy to the system periodically. But it turns out I was very surprised when it turns out that when we define the pseudo spectral form factor from these pseudo energies, it works, right? I mean, not that it works, that it describes, it has the same features of the normal spectral form factor, right? And that it displays some ramp if the system is chaotic. So it was also, I would say, striking for me when I realized, right? Okay, so we do the same that we were doing before. So we take these exponents at this time scale that we are interested in and plot it as a function of the inverse temperature. And this is what we find. We find that essentially both regimes, like chaotic and non-chaotic, get very close to saturating the bound. So we conclude that the saturation or not saturation of the bound doesn't have to do with chaos, but rather with other features. And we again see the saturation at time at high temperatures, right, at infinite temperature. And why? Because this spin system has a dimension of the Hilbert space 2s plus 1, so it is again finite dimensional. So we have the same argument as before, right? That there are some finite amount of levels, and until some, I mean, there is some energy in which the levels are not accounted. I mean, you do not change anything in the thermal average. Of course, we have some dependence on the specific dynamics of the system, if the system is chaotic or not chaotic. But this is like an intuitive idea that one can use.
Sorry, Pablo, just a small
Yeah.
question. Does the non-chaotic system here get closer to the bound? than the
Yeah,
chaotic one?
actually, I think it does. That is something we didn't we didn't do a plot in which we show how close we get. I mean, specifically like the distance to the bound. But I mean, it turns out that it gets closer than the chaotic system.
But is this just a fluke in terms of the system, or is this something interesting here? Or is it just
I think this is just. I mean, actually, I don't know, because to really be able to say something, if non-chaotic get closer to saturating the bound, one should study many different non-chaotic systems, like to really see the properties. But I think it just states that, or what the interpretation I do from this plot is that both of them get very close. I don't know if that it gets a bit closer in this case, it's a signature of something. It can be interesting to study more, I would say, but what the interpretation I do from this plot is that regardless your dynamics, you can get close to saturating this bound, and therefore that the bound is tight can give you insight, right? On just knowing the bound, you can know something from the dynamics, maybe know something from the dynamics that you couldn't on the other hand, because it would be very difficult or something. Yeah, but it is something striking to me too.
So Pablo, in practice, the bound is only, you say it's saturated, but it's saturated over 1 decade, right? Of regime of temperature. It's not saturated everywhere.
No, it's not saturated everywhere. But still, for example, when well, actually, I think you could argue that, of course, this is everything finite size, right? So I think in the thermodynamic limit for these systems, right? So when you take either S or the dimension of your random matrix to go to infinity, I have some plots on the scaling of this, and you see that as you increase the dimension of, say, your random matrix, the region in which you see close to saturation is bigger, right? So in principle, when n goes to infinity, this should be yeah. I think in the thermodynamic limit, of course, not at very low temperatures, but yeah. Well, actually, let me show you the plots I'm showing. Well, maybe I will show them at the end, just to keep it like this.
But is there any reason why this is, this specific decades between beta and 10 minus 1 and 1, where you are so close to?
I don't have a reason for it because
it's the same range as the one you showed before, right?
yeah, it's a very similar range to the one I showed before. I think maybe I don't think there is a deep reason behind that. It's just that the sizes I could handle in my simulations were similar for the like I was able to study kind of similar sizes in both systems, and I think that is why it happens. But yeah.
But isn't there just I mean, just count the timescales in your system and just
yeah, actually, I mean to do a if you want extensive study of what is the region in which we get close to saturation, how close we get. I should take into account the specific units of time, the specific units of inverse temperature. Like this is a bit if you want h bar kb and everything equal to 1, but yeah, I don't know. I don't think there's a deep reason for that, but I don't know. Okay, so let me just recap.
I have a question.
Sorry? Yeah.
Can I ask a question? I have
sure.
two questions actually. So first, if you go back one slide, you had these oscillations there in the chaotic and non-chaotic cases. So do you expect the bound also to hold on the oscillations or not? Is it only the initial decay where it holds?
I think it only holds in the initial decay. I think so because.
So which one of the assumptions is doesn't hold in the after decay transient?
First, I don't know how. I mean, of course, you may be able to fit a decaying exponential in this part over here. You may be able, but it may be more difficult or depend a lot on how you average or something like that. But I was thinking of trying to see. I mean, if we could use this bound for oscillatory functions in general, which it was something I was thinking about, and I think the main problem with the current derivation of this is this restriction here, that you have that the function in the real line is real, because if not, you could consider functions like here, like an imaginary exponential, right? So you can consider, but this does not obey that property, and that property, I mean, it's not very important. Well, actually, here there's a typo. It should be a square. It's not very important, but it's just to be able to split this in a easier way, to split this 1 minus and the function square, because if f is real in the real line, you are able just to do the typical product of difference. The a minus b times a plus b, right? The typical formula. But I think it can be extended. I don't know how, or I have not yet looked into it.
Okay, so some of the oscillations in your plot look like they might be steeper than your bound. So
I think actually, I mean, to study those oscillations, let's say here, it's I mean, it's actually, I don't think it's so. In this case of the quantum kick-top, you have to think that really I'm doing the times that you are working out in the beginning, right? Here you are working in discrete times, right? And here you are extending it to real times, to any time you want. Like here, this works period by period, right? This gives you an stroboscopic description period by period. And I think here we are extending it to real time. So I'm not sure that the extension to real times is captures the same features, you know? Because maybe, for example, if you were studying those fast oscillations here in random matrix, you know, you would have essentially noise over here, right, over this line. So I don't know if what you're going to study there is so, or will be so as well defined as what you studied from in the beginning, right? Because
why? How do you know that that it's well defined for short times then?
Because what I was, I mean, these averages that we are doing, what I said at the beginning, that it is not self-averaging. If you do just one realization, this part is always well described. Yeah, you know, you see the fast oscillations in the ramp and in the plateau. That is the region where you see the fast oscillations. So I think that is why to study the bound outside of this region, one would need to be very careful in how you define this noise, if it is even physically makes sense to study things on this noise, because yeah, you have in quantum mechanics you have an intrinsic noise, you know. So I think to study things in this region would be, I mean, one would need to work with a bit more of care. I don't know if that answers your question.
Okay. And then for the bound, there's an H bar somewhere, right? Because the units don't.
There's an H bar. Actually, I have not yet changed this in the presentation, but we were thinking of changing it in the paper. Like everywhere where there is an beta, should be beta times H bar.
Okay. All right. Thank you.
Thank you. So lastly, the last thing I want to do is to compare this with other bounds, right? In particular with quantum speed limit. So let me give you a very brief idea of what is a quantum speed limit. So we know that we know from the beginning of quantum mechanics, Heisenberg's time energy uncertainty relation, right? It states essentially something like this. But we also know that this cannot be understood in very firm ground, because time cannot be understood as an observable in quantum mechanics. So you may have issues when trying to understand this in a more firm basis. So to do so, what people did is say, okay, let's shift the interpretation that we do of this inequality. Rather than being a statement on a measurement of observables, it's a statement on the intrinsic timescale of the system. And to formalize this, Mandelstam and Tam derive the first quantum speed limit. So essentially the idea is that the minimum time in which you can go between two orthogonal states is given by an expression like this, which essentially contains the standard deviation of the Hamiltonian. So it's very similar to the Heisenberg's uncertainty relation, time energy uncertainty relation. Also, with time, people realized that there were some issues with this bound that may not always be physically relevant, this Mandelstam-Tam bound, and they derived, Margolis and Levitin in the 90s, they derived a different bound this time depending on the expectation value of the Hamiltonian. So it turns out that the real quantum speed limit is given by the maximum of these two bounds. And one can also think in a complementary way. Instead of bounding setting a minimum time in which one process can happen, one can think of setting a maximum speed at which one process can happen. So since the fidelity, I can give more details on this also if you want. Since the fidelity is kind of a distance in the Hilbert space, so it gives you some distance between quantum states, its time derivative will represent some speed, right? So we can bound this time derivative of the fidelity for pure states. It is done between many other things in this paper by Aurelia Adolfo with Margolis and Shanahan. It is bound by this expression, right? So why are we interested in this at all? Because, as I told you, the spectral transfer factor can be understood as a fidelity between two pure states. So this gives us some quantum speed limits on the spectral transfer factor directly, without needing to do any derivation or anything. So one finds that the time derivative of the spectral transfer factor for the harmonic oscillator, we only did it in this case, is something like this. So this is the bound and this is the time derivative. It's not very tight, but it is easy. This is why we studied it and compared it. So since we have a bound on this S dot, we can also have a bound on the inflection exponent, which is essentially this orange line that I'm showing here, right? So we see that our universal bound is tighter at high temperatures, right? At low temperatures, the quantum speed limit is tighter. And why I'm here, I can give some, stress out why is our bound universal, because it only depends on temperature, right? While this depends on the specific properties of the system, right? The fine structure, how you define this delta E and so on. So it will not, I mean, it's not universal, this quantum speed limit. This depends on the specific properties of the system. Also, in the spirit of these quantum speed limits, Batakaria,
that you can apply you can apply the quantum speed.
Sorry, I was.
I mean, I'm not hearing if there's something.
You should just continue. It was just missed.
Okay. Yeah. So, in the same spirit, by Batakaria, it turns out that if your fidelity is between 1/2 and 1, you can show that it is lower bounded by this exponential, right? And it turns out that for the spectral transfer factor for the harmonic oscillator, we obey this property. So we find another bound, also system dependent on this eta exponent. And I don't know if you are seeing it well, but it's this dashed line over here. So again, it's our bound is tighter at high temperatures, right? I'm not claiming that our bound is tighter than any quantum speed limit, because one could try to look for very tight speed limits for the spectral transfer factor. I'm just claiming it is tighter than these two that I have studied. So with this, that was everything I wanted to tell you. I hope it was not boring and informative. And so let me conclude, and then if you have some questions, I'll be happy to answer them. So the two questions I posed at the beginning: can we find similar universal bounds? Yes, we can, and we have found them in the spectral transfer factor, but I think there's room for finding them in different contexts. Do they only apply in the chaotic regime? No, and in particular, neither is the saturation of those bounds only present in the chaotic regime. Here is the comparison with other bounds. As I told you, this analyticity bound is universal because it only depends on the temperature, while this depends on the specific system that you are considering. And I want to end with this space of boundable quantities by analyticity, right? So we have here the autops. I hope to have convinced you that we also have here the spectral transfer factor. But I think there's plenty of room here to find other bounds. We just have three conditions. I don't think they are so restrictive. We can even try to manipulate some of them. So with this, thank you very much for your attention. And if you have any questions, I'll be happy to answer them.
Yeah, thanks a lot, Pablo, for the talk. Does anyone have any question? Okay, maybe then.
Just to.
Yep.
So Pablo, just again to take. I mean, I don't really do quantum stuff. So, can you just sum up like the key physical approximation, or the you have this there's formalism and it rests on some physical approximation. Which one is the key one, I guess, as the question, and how does this limit the universality of?
I mean, you say in the bound that we have derived.
Yes. Yeah.
So I think, yeah, I think this goes down to these questions. Yeah, to the three properties I was saying before. So, I mean, first of all, of course, we are working in the quantum world, and
well, semi quantum, right?
Yeah, well, actually, I think it's truly quantum because what goes through the semi-classical approximations and so on are the connections with classical chaos. You know, like nowadays, I think once that the main features of quantum chaos were established, people started to work in systems which do not have a classical limit, right? Many body systems and so on. And they say, okay, if they show the features that we know that this presents, they are chaotic, right? And they may be totally quantum. And I think, I mean, I have to be honest in the sense that I have not studied the boundaries of, I mean, where do my approximations work? Because, for example, here we have one approximation that of long times, you know, so that we make this inequality time independent. Because if not, we may have some. We also have one big approximation, I would say, when we argue that this f has to be smaller than one. So we have to be able to normalize it, which I was saying it essentially, yeah, here. And then also. Our thing, I mean, this exponential decay that I'm talking about only holds for some small window of times. So I don't think it holds everywhere. So I think those three would be like the three main issues to point out. Also, there may be issues, we are thinking about this, about the considering multipartite Hilbert spaces, which may give you some trouble.
I don't know what that is, but
no, like consider two copies of instead of one copy, consider two copies, right, of the same Hilbert space. So I think those three plus the thing with multipartite, I think those would be the three main flaws. I mean, not flaws, but like the weakest links, you know, like the things where you could aim for breaking the results. I don't know.
Any more questions?
Well, just a curiosity for the structure factor in the random matrix model, you should be able to get it analytically, right?
Yeah. I did not show the specific. I mean the analytical formulas because they are not. I mean, some of them are nice. They are given in terms of. You can look at this reference. I mean, in this reference, this is done for any, no matter how big is your matrix. It can also be done considering large n, like some perturbative expansion, and this is also related to the literature on random matrices. And yeah, I did not give them because they are a bit. And one in particular, the part in which this grows is, you know, like a sum of Laguerre polynomials, generalized Laguerre polynomials, which is, I mean, it does. I didn't write them because I don't think they add much to the physical intuition. But yeah, you can work them. The only thing is that I don't think you can find an analytic expression for this eta. This eta, I think, has to be worked out numerically. Maybe also from the analytical results, but numerically because you get some equations which I don't think are solvable. So,
but eta, it's basically a fit, right? To get
it's basically a fit. It's basically a fit, yeah. But of course, it also has a definition right from this as the maximum of this quantity, you know, S dot over S. Yeah, you can by the argument of where does this exponential decay hold, you can get some expression for of course from the fit, but also analytically, like the maximum of this quantity, or the minimum if you don't put the absolute value.
But this relates to the question of Jan, because if you don't have an exponential fit, can you still work with that definition of
I don't think the bound gives you anything interesting if you don't have an exponential. Maybe what is true is that maybe if you think of different, you know, in the end you have here it's a bit hidden, but this map gives you a lot of conditions. You know, like it is essentially what gives you the structure of this inequality and so on. So if you include a different map, you may be able to not only consider different shapes of the thing in the complex plane, but also include different decays, different regimes. Your function may be, I don't know, some polynomial. But I have not looked into that. Maybe there's room for that, but I'm not sure. I know that the one that works easy is that if you have an exponential. If you have an exponential, real exponential, you can do things.
Okay, thank you.
More questions?
I don't know if Alessandro is talking.
Alessandro, are you saying something, because we are not able to hear you? Alessandro, if you are saying something, we are not able to hear.
Yeah, we are not able to hear it. Yeah.
So he's going to ask on mine, so just
Thanks.
Okay. No.
So the question is if you can relate why the ramp in spectral factor is related to chaotic behavior.
Okay. Yeah. It's a good question. The thing is that we studied some easy versions of that. So the idea is that I think this would be better if I share them directly the results we have. I think it's here. So this we have some way of understanding them from the it's here. Okay, so these plots may not say much, but the idea is that if you have so here I'm doing the spectral form factor, right? And putting the contribute this line, this violet line is the contribution from the nearest the first level spacing. So the one I was showing before, where I'm checking the difference between the two consecutive the consecutive energies. The next one will be the difference between second neighbors in energy. The third, okay. So there's a nice way to understand this ramp, because if you just input your level spacing from, say, nearest neighbors, you will find something very similar to this, right? And the farther apart that your neighbors are, the sooner they contribute to this dip. So the idea is that this ramp is, if you want, a sum over all of these smaller ramps that you have from different correlations, and they in the end add up to the ramp that you have. If you consider this is at infinite temperature, but if you consider a smaller temperature, it is very nice to see that the contribution from the nearest, the main contribution is that from nearest neighbors in energy, because the other ones are like your system does not have enough temperature, so to reach farther neighbors, right? And the contribution is coming mostly from the first neighbors in energy. I don't know if this gives you some intuition, but I think with this you can see that if you have the behavior I was showing before on the level spacing distribution, you can you directly get that this spectrum for factor decays and then grows in a ramp. Okay.
Okay, more questions? Okay, if not, then let's thank Pablo for his wonderful talk. It's a quite long time. He needs some rest.
Yeah.
And you can talk afterwards about the discussion.
Yeah.
And thanks a lot for the first commencement session of the LuxStat Mech seminar.
Yeah, thank you for having me, and for the nice question. It was very nice. So yeah, I'm open to discussions if you want so yeah.
Yeah, okay.
Okay. Thank you very much. Bye bye.